The labels of many diet soft drinks contain warnings about phenylalanine, and the structure of phenylalanine is shown below. What is the structure of phenylalanine at pH 13? So what we're doing here is we're evaluating how the pH of the solution affects our acidic hydrogens. So this is drawn in the acidic form for the two different acidic hydrogens that we have on phenylalanine, which is an amino acid. So we need to know some key relationships about pH and structure. So from general chemistry, where you talked about this would have been in the buffers section. And so with your pKa values, right, you probably remember learning that a good buffer solution is if you're trying to buffer that pH at close to or equal to the pKa value. And that's because when your pH is equal to your pKa, you have equal amounts of acid and base. And so what that means is you're talking about the acidic and the basic form. So if you're talking about the carboxylic acid, that would mean you have equal parts of the protonated carboxylic acid and equal parts of where you don't have that hydrogen and you have the anion. And that makes a good buffer solution because you have acid to deal with added base and you have base to deal with added acid, and you can kind of keep the pH roughly constant. Okay, so that you might remember from general chemistry. So what we're doing here, we want to take this a little bit further and know that if the pH is less than the pKa, so if the solution is more acidic, most of your molecule is going to exist in its acidic form. So we will just say exists in acidic form. So that means if the pH of our solution was lower than 1.8, we would expect to see the carboxylic acid protonated as it's drawn here. At any pH above this number, above 1.8, we would expect it to be deprotonated, okay? So let's write that down here. So if your pH is greater than the pKa, it will exist in the basic form. Okay, so since we have a pH of 13, right, so this is lower than the pKa, or lower than the pH, so that means that it's going to be deprotonated. So this will exist in the basic form. Okay, and so we're comparing each of these individually. Okay, and then we look at this protonated amine and we notice that 9.1 is also lower than the pH. So this will also exist in its basic form. Okay, so the basic form here of your carboxylic acid is the carboxylate, the anion is the basic form. And if NH3 plus is the acidic form, the basic form here would be the neutral amine. So that means that we are looking at A. So you've lost the acidic proton from the carboxylic acid, so you have that carboxylate, and you lost the proton from the protonated amine to give you the neutral amine.